Welcome to everyone. Thank you for joining us for this meeting of the ACT section of RINA. My name is Warren Smith. I'm the current chair of the ACT section, and I'm currently sitting in my office at ADFA at UNSW Canberra. Thank you to Lily for all of her organisation to organise this meeting, and of course thank you to John, who's agreed to speak to us tonight. John Kecsmar, if I've got the pronunciation close to right, I'm not sure, studied at Solent University and then later Southampton, founded his own company, Ad Hoc Marine Designs, in 2005 after spending time with Babcock Marine, Austal and Wavemaster. He's certainly been significantly involved in RINA's organisations and committees, the High Speed Vehicle Committee, and as a fellow of RINA. Sat on technical and editorial boards for RINA and also for Lloyd's Technical Committee and High Speed Vessel and Safety Committees, SNAMI engagement. So he comes to us with a huge array of interests and experience, and we look forward to his talk tonight, interestingly titled, as he's shown on all of our screens, the good, the bad and the ugly of the structural design and fabrication of aluminium high-speed vessels. So I don't want to steal any of John's time nor his thunder. So John, we look forward to what you have to present to us, and thank you very much as my lights go out here. Over to you. Thank you.
Thank you, Warren. Well, good morning, good afternoon and good evening, everyone. Well, obviously the title. Why the title? Well, just like any good Hollywood spaghetti western, it's always full of some good actors and some bad actors, a few ugly ones, and of course, a smattering of cowboys everywhere. And I thought, well, that seems rather appropriate because in the last 30 years, I've been designing high-speed vessels. That sort of sums up this industry. So how do we differentiate something that's good from bad? Is it good design? And what does good design mean anyway? And what about good fabrication? You could actually sort of say, well, if we had the best design in the world, but built by the worst fabricators in the world, or conversely, the worst design in the world, built by the best fabricators in the world, what would the result be? Well, probably similar to each other, and in reality, probably wouldn't last very long. So what else is there? What about quality? So is quality part of the mix? And if so, how does it influence all this? So let's look at design. Of course, we all design vessels to class using the class rules, but class rules only provide the minimum standards to satisfy. I shall repeat that, the minimum standards to satisfy. So often I hear people say, it's the gold standard we're designing to glass. Well, no, it's actually the minimum standards to satisfy. And similarly, class rules do not imply any fitness for purpose. You can thumb through the rules if you like, and there is no rule that allocates anything related to fitness for purpose. Similarly, there's no guarantee of longevity, even though by implication there is this, simply because the rules are related around a particular stress value, and that stress value, so long as it is not exceeded, is going to imply some kind of life. But that's about all. And class rules cannot be expected to cover all the design issues. Why should they? It's not their job to, because if they did, there would no longer be an independent society. They would then be having a conflict of interest with you as the designer. So surprise, surprise, design is the responsibility of the naval architect, not the classification society. So when designing to class rules, it can throw up some quite peculiar results, notably in the terms of shapes. So if we start looking at the general anatomy of a ship structure, we have transverse frame, We have longitudinal stiffeners, transverse spacing, stiffness spacing, a support area, and of course the associated spans for each. So when you start to plug all that into the class rules, and if you are designing to just minimums, you can end up with some quite peculiar shapes. If the shape of your hull is like shown on the screen on the left, you can actually get very deep bottom frames, but very slender side frames. Similarly, you could end up, like on the right-hand side, slender bottom frames and very deep sides. But what this results in is here. There's a major change of structural stiffness. So where are class rules to guide you on that? Well, there are none, because that's your job as a naval architect to understand the implications of what it is you're designing. Over the years, I've been invited by yards across the world, as well as clients and designers, to sometimes comment on some of their designs which have had perhaps a less fruitful history, shall I say. And time again, I do see it, because here, this is from a patrol boat I was asked to have a review of. Typical slender side frame and a very, very stiff section here. And surprise, surprise, they had problems. And this is not just limited to detail frames, because if we take a step back and look at this on the global level, I've just stolen this picture from the Type 31 frigate. If we were to draw a graph of stiffness along the entire hull length, it would look something like this. We can see that in way of the deck house or the superstructure, there's a major change in structural stiffness. And as such, just like the frame, where there is that sudden change, there's going to be a major change of stress. Therefore, the role of the naval architect is to understand the implications of this, because it's not in class rules. And by way of a very simple example, here is a lifting lug, and it has a very, very high concentrated load. So just like changing the stiffness, how do I change the load so it's going to be distributed nice and smoothly? Because when we see that we're going from a 30mm plate down to 5mm, we can't really just butt the 5mm into the 30. That's quite ludicrous. So what we have to do, we have to calculate the available shear area in both the weld length and the amount of metal you have, and then doing so, transferring down to 20mm plate, and then again down to 10mm plate, and then of course eventually down to 5mm plate. So simple things like this are quite important, yet quite often they're overlooked. Today we can use FEA to provide further guidance for us. So here's a simple catamaran that's been subjected to a global load. And from this, we can quite easily identify locations that do require some attention to detailing. So when we come to draw up the frames, we know, well, near the bow or near midships, there's a particular region that requires a bit more attention than all the other frames. We can create a generic idea of what frames are like. There's ostensibly the straight line method, and there's the more curvy method. And if we take the straight line method, this is very good for production, because you can simply use extrusions and just weld them together at right angles or whatever angle they're at, and simply put in a nice bracket. Whereas on the right, this is nice and curvy, it looks good, but it does actually require a little bit more effort, because you have to produce the actual cut part, and that takes a bit more time. And then once you've done the cut part, you then have to bend and roll the rider bar, so there's a little bit more time involved. But each have their own merits. But in terms of design, what merits do they have? The Japanese in the 1980s, they also asked this question of themselves, and they were looking at frame designs for various large vessels like container ships and tankers and bulk carriers. And so they came up with a series of very different types of connection, and they tested them to failure. And they established a stress concentration around the failure joint. failure of the joint. And in this instance, the stress concentration factor is just over 4, whereas on the left, it's only just over 1. Quite a big difference. And so quite clearly, the shape of your frame can change the amount of stress by quite a significant amount. So that's something you need to bear in mind, not just in terms of cost. And then if we go down even further, if we go down to the type of shapes that you're choosing for stiffening, we can see here on the left, the angle bar. If you take an angle from where the web butts into the plate, the subtending angle is 54 degrees. And even still at that angle, the torque cannot actually get inside. Whereas in the bowl bar, even though it's 78 degrees, the torque can quite easily get into, well, the inside of the web of that bowl bar. So clearly the angle bar, the welder, as he rotates his torque to try and weld the inner face, is not going to get a very good quality weld. If we take that one stage further, here we have what is a T-bar, but it's actually longitudinal, and it's passing through a transverse frame. For whatever reason, the designer decided to specify welding the flange of the T directly to the web of the transverse frame. But if we start to analyze this, why did he do this? Well, I suppose really when you consider what is the objective of it, and quite clearly it can only be to transfer the shear load from the longitudinal into the web. However, if we look at this somewhat pictorially, we can see, okay, we have that transfer of the shear, but as the longitudinal is bending, there's also a tensile load in the flange. So suddenly this weld that perhaps was only designed to carry shear is now having shear and tensile and is a biaxial stress raiser. And not only that, the resultant load is quite possibly much greater than that was what was allowed for. Fabrication. If we look at tempers of aluminium, in this case 5083, and very simple stress strain curve. If we are to plot on here O temper, it has a yield stress of 125 MPa. And then when we compare this to the UTS of 305 MPa, there's an overload. I like to consider this the ratio between the UTS and the yield as a percentage in terms of how much capacity that the temper can adopt before it reaches its critical limit. And in this case, it's 144%. So in reality, that's a built-in factor of safety of 2. And it is the very reason why the UK Ministry of Defence, when they specify building with aluminium, it must always be O temper. Whereas common tempers used today are H321 because they have that higher strength, in this case 215 MPa. But you can see the overload is reduced by a factor of 3. That's quite considerable. So that means any overload beyond the as designed 215 MPa takes it closer and closer to failure. It has implications in terms of fabricating the plate. We can quite easily work out what is the minimum bend radius possible by the very simple formula. It's just related to the yield stress and the thickness. So in this case, if we assume 6mm plate, the minimum bend radius is just over 1600 millimeters. The H321 is just over 900 millimeters. So that's quite an appreciable difference. What this really means is that any value below this minimum possible bend radius is going to start to work harden the alloy beyond its original temper. So the tighter the bend radius, the tighter the the greater the strain hardening experienced by the alloy. And we can see this shown sort of pictorially here. If we assume the little black dot there is O temper as you're starting to roll it, bend it, and form it as shell plating, it's going to slowly go around the stress strain curve to approximately somewhere around about here. Whereas the H321 probably starts approximately in that location. And then as it's rolled, goes up to much higher on the curve. So you can see, even though the grain structure is actually decreasing and increasing in strength, you're reducing that ductility and also getting closer and closer to possible failure. This has quite serious implications when you're fabricating structures like water jet ducts. Because as you can see here, there are multiple small radii. So extreme care and attention must be paid to the rolling and the forming of the plating when making the jet duct. And it also implies really you should use O-temper. So what about quality then? Well, is this a piece of quality? This is taken from an old slide I once did. And when I was a student in the 1980s, this was a Skoda, and it was the butt of all jokes. It was a terrible car. One of my friends had one. It was just appalling. And there were so many jokes going around, like, what do you call a Skoda without a roof? A skip. But the interesting thing about all these cars, they were still roadworthy, therefore still legal. Only just, but they're still legal. So is this a bit of quality? Well, visually, it looks infinitely better than the previous car. But you may be surprised to know this is actually the very same car, just 20 years later. So quite clearly, there is something to this thing called quality. So how can we define it? Well, Maslow decided man is a wanton being. There's always some need he wants to satisfy. And once this is accomplished, that particular need no longer motivates him, and he turns to another, again seeking satisfaction. Now, from my point of view, the key thing to take away from this is the motivation and the satisfaction. So how do we relate this to shipbuilding, for example? Well, we can break down quality into two very distinct fields. The first one is quality control. And this is quite simply detecting. So you're trying to measure something. Is that really a form of motivation? And the other field is quality assurance. In other words, just preventing non-conformity, making sure that you're supposed to be doing what you're doing. Is there any satisfaction in this? Well, that's really almost a philosophical question, and that's really related more to the shipyard and how they train and motivate and educate their welders and fabricators. That's not really for me to say. However, whenever I do go into some shipyards, some things become quite obvious to me. I hear phrases like, we have a quality system in place because we build all our vessels to class. Oh, really? Excellent. And then we have the class of A inspects and approves all our fabrication. Oh, well, bully for you. Jolly good. But from where I'm standing, this is all reactive. It's not proactive quality control at all. So where is the motivation and satisfaction? Other than someone else is doing the job for you. So if we look at what class says about such things, and here's an excerpt from DMV, and it's all about visual examination and radiographic examination, and it refers to having 2% to 5% of the total weld length. What I take away from this is not the 2 to 5%, it's actually the opposite. I see it as 95 to 98% of the weld are not tested. And when you consider that most of the ship's structure consists of fillet welds, how are you going to x-ray them? You can't. So you're relying upon purely visual examination and at times perhaps a bit of penetrant testing, because only butt welds can be x-rayed. Some time ago, when I started doing my PhD, I conducted a series of experiments, and I wanted to see the effect of the quality of the weld and the effect on fatigue life. So I prepared a whole series of joints, and this one in particular, this is a standard clean edge prep wet joint. All the welder had to do was just weld it using his skill. And visually, this is an acceptable butt weld. And here is the X-ray. And as you can see, is just an extensive lack of fusion. So it failed the X-ray. And then, well, what about this? Where is grinding off the dirt and the oxide layer? Why hasn't the welder suddenly stopped to think, well, is this something I should do? Ah, it doesn't matter. We built a class, it should be all right. And what about this? You've got a butting of a rider bar into another one, and it's missed. And so the welder decided to just fill it with lots of, well, weld. And surprise, surprise, because there's so much weld there, as it starts to cool, it's shrinking. As it's shrinking, you might just better make out there's a hairline crack there. And what about this? This is monstrous, utterly appalling. How on earth this is allowed to continue is just beyond me. So when does visually acceptable become unacceptable? So quality, is it really important? We can see here in this region, it's a beauty. There are just too many stop-starts. And we know stop-starts are notorious for cracking for several reasons. If the welders put too much heat in at the start or the stop, then you get a crater crack. And so it doesn't take too long for that to start to initiate as a real crack. And also, if the welders are perhaps a bit too lazy to grind over the stop, there's going to be some natural crack behind it because there's going to be some lack of fusion. And there is an oversized fillet, which indicates the weaving because of just poor lineup. And then here, we can see also something very similar. There's the lack of fusion. It's all cold and blobby. And as our QA manager used to say to me, it's rather like blobs of snot. And it's quite an apt description. And then there's lots of black soot everywhere. And that's just a general loss of gas shield. And overall, it points to just very poor preparation. But what is most surprising about this, it was passed by class. Do you think building to just class is enough? So shipyard quality, it is not the job of the surveyor. So now we come to the most obvious, the elephant in the room. And that's of fatigue. Fatigue is rarely one single obvious flaw that causes failure by fatigue. It consists of a long chain of events where each on their own may not be significant. But just like the mechanism of fatigue itself, it is the culmination of many small events that lead to that failure. And this is the start of one of those chains. Here, this is the material aluminium against steel. And now we can see that steel has an endurance limit, whereas aluminium does not, which means the more you flex it, it's still eventually going to fail. And the stress at which it's going to fail, it becomes less and less. So when I was a young graduate, I was thinking, gosh, well, what do I design to? And I did some research, and I was tasked with designing the water jet ducts of some of our vessels. And I found this, at the time, unpublished US Naval research, and they did some very simple tests of welding 5083 aluminium. And you can see here that the class approved base values are, as you'd expect, around the 120, 125 MPa. Whereas once they're subjected to an environment like seawater, there's a significant reduction in the amount of allowable stress. by anything up to 90%. So I took this on board and decided to design my water jet duct to this very limit of 10-20 MPa. And here is the resulting finite element analysis that I did of the water jet duct. And this is over 25 years ago. And I decided to just keep changing the structure until I actually got a value of around about 20 MPa. As you can see in the top right, actually got 21.7. So I thought, that's good enough for me. Because it's not about the absolute value, it's about the trends. All we care about the trends. I then took this to the next stage because we have to weld the flange, which takes the mating surface between the actual jet bucket itself to the duct. So here you can see there is a solid model of the flange, which is then welded to the actual duct itself. And I modeled the weld and I calculated how to apply the bolt forces onto this flange and then worked out what the stress is. But as you can see here, the stress is actually quite high. So I was wondering what on earth we can do about this. Well, there's two things we did. Well, in actual fact, three things. The first thing was, as you can see on the left, we created a J-prep. And we conducted a series of tests to see how much of the geometry of the J-prep we need to ensure that we had a very good penetration and how many roots and how many caps are required. On top of this, decided to change the type of gas we use, change it to HeliShield. Why HeliShield? Well, quite simply because it burns much hotter and it gets a better penetration. Also, in combination with 5356 filler wire rather than 5183, you get a much better quality weld. And on top of that, we decided to just here do a little undercut of the toe of the weld. I looked at many research papers and they're all suggesting to me the same thing. If you can undercut the the toe of the weld, you can improve your fatigue life. So that's what we did around the entire circumference of the jet duct and also on the transom itself, because the transom was only 6mm plate. It was just a diaphragm. It was flexing. But this then starts to bring us on one other long chain of these events. The temper's influence on the fabrication. Because how do we actually improve the mechanical strength of the alloy? And this is by simple strain hardening. And it is achieved where the alloy is rolled and it's worked by some mechanical means under an increasing pressure. And this uses the slip planes within the alloy matrix to dislocate and move the crystalline structure to become much closer together. What this means is that the dislocations then become entangled with each other, thereby forming obstacles to further dislocation motion, and hence they increase the stress. But also it reduces that ductility, as I was mentioning before. Well, the reason why this is quite important is it's actually very, very familiar. And why is that? Because when we look at how fatigue starts, it's the very same mechanism. The initiation of a crack involves the localized movement of dislocations along the very same slip planes that you're using to mechanically work the material. So the same slip planes that you're using for strain hardening are also the very same that are used in the mechanism, if you like, of crack initiation. So this means, for example, when you're starting to roll that plating for the jet duct, if you leave just even one small score mark, no matter how small, that is another dislocation. And so as it starts to flex, you're going to get under a microscope something that looks like the top image or the bottom image, where you can see the intrusions and extrusions of where the metal is actually, or rather the atoms are moving against each other up and down, rather like having a whole ream of paper and you're just sliding it back and forth in your hand. And this constitutes what is termed crack 1 stage growth. The initiation then goes to 2, then eventually failure in 3. Now, fatigue failure in aluminium is a voluminous subject on its own, and there's just simply not the time for me to discuss it all. However, what I can point out are some various obvious issues. What we can see is that the larger and larger the weld bead, this reduces your fatigue strength, simply because you have a localized greater stiffness, relatively speaking, again, between the weld and the parent metal, just like the frame, just like your superstructure. So there's a stress concentration. So therefore, if you're over welding, you're actually making the situation a whole lot worse. Similarly, with misalignment, just a simple 10% misalignment of plates can result in adding 30% to your stress concentration factor. Similarly, if there's a mere 1 degree angular misalignment, that also adds another 30%. If you have the two together, that's actually 60%. So suddenly that weld is no longer performing as you had designed it. It's actually experiencing stresses of 1.6 times that of what you've designed it for. So with all this in mind, I thought, well, we need to actually do something about this in production. So I decided to change some of the basic procedures within production for the quality control, and to ensure that any non-conformity and any particular errors came back to me, and I would go down and approve them. And I wanted the production to adhere to strict quality control. Now, full credit to production, they took it on board and they did very, very well. However, the production manager, he was less than impressed with me, because all he saw was just a rise in hours, and it became a bit of a battle, but in the end, only just I won. So was it really worth it? Well, here we are. This is one of our vessels, the Hong Kong Tricats. She's a 45 meter, carrying some 350 passengers, and she travels at 45 knots. She runs between Hong Kong and Macau, and she runs between 12 to 18 hours a day, and she runs about every 15 minutes. And she's been doing this for over 25 years now. And to the best of my knowledge, there's not been a single structural failure of the water jet ducts. More so, there's not been a single structural failure on the entire vessel itself. So in terms of the production manager criticizing me for increasing what he saw as production man hours, there were no hours at all relating to warranty or rework whatsoever. So where is that saving now? We had another shipyard build one of our jet ducts. And bearing in mind, excuse me, the water jet duct called up for the joint of having a root and 2 caps. And as you can see here, there's more caps than you can shake a stick at. I'm sure Shane Warne would be impressed with his number of caps. So is this gap filling? Is it acceptable? Well, surprise, surprise, as we've already seen, poor quality and poor adherence to any kind of quality control, you have lack of fusion. And you can easily see the porosity. You don't need to look under a microscope. And so, surprise, surprise, it failed. And it failed with just I think about 2-3 weeks of service. It's appalling. So bad fabrication and bad quality equates to reduction in fatigue life. However, today, there are means and methods to try to address this. There is a fatigue analysis method by the International Institute of Welding, and they've spent some 10, 20, almost 30 years now performing a lot of R&D. And there's essentially 3 routes that the naval architect can take in order to assist in this particular process. And they are termed the nominal stress approach, there is a hotspot stress approach and the not stress approach. The problem I have with this is that whilst they're admirable on their own, they're all a little bit abstract and a bit too much absolute. And I find that people often refer to the values that they calculate as being the be all and the end all, almost as if that's it and that's all that is required and sufficient on its own. Moreover than that, the calculation is all about the stress at the weld toe. That's all. There's a lovely paper that was published quite a few years ago now, and the author decided to check some of the validity of some of these methods. And what he decided to do, he took a standard frame for a container ship, and he investigated various rules and various methods, whether it's notch stress, hot spot stress, or nominal stress, and performed the calculation based upon the various methods. And the very same joint, the fatigue life ranged from 20.6 years down to 1.8. So with this degree of variance, how on earth can he actually have any confidence? So when someone says to me they've calculated the fatigue life to 20 years, well, how much confidence can you really place in that value? Because there's a lot more to it than just the calculation. But we can actually start to address this. Again, another one of these long chains of events. Here, this is an FEA analysis I did with a bowl bar running through a transverse frame. And I wanted to have a look at the stress distribution between the welded joint of the transverse frame to the weld, to the shear of the bowl bar. We can see here that at the bottom there was a compressive stress of 9.5 MPa, and all the way at the top it went to 5.5 tensile. Then as the welder goes around the top, there's a peak of 10.5 MPa. So that seems fair enough. However, with a little bit of tweaking, changing the shape, as we've already seen with the frame design, I just altered the shape of the mouse hole. And we've gone to a reduction of 6.8 compressive strengths. But the important part is, at the very top, it's now down to 2.6 in tension, and then around at the very top, down to 5.8 MPa. So suddenly, I've actually reduced the amount of stress by 100%. So by implication, I've increased the fatigue life by a factor of 2. So is it really worth going through this very long fatigue calculation? Well, on the one hand, yes, but we need to consider all of these events, all these chains that link together, and see what we can do to improve matters. And this is one of them. I was faced with a very similar dilemma when we were asked by Lockheed Martin to design their swath slice vessel. They approached us owing to our expertise in swath designs and aluminium fabrication and design. So I was wondering, well, what do I do here? Because I have 4 very slender hulls and there's a bit of a bottleneck. Because we can see that as you apply the nominal half draft classification society load just here, what's going to happen? Well, around the thin strut region here, there's going to be a lot of stress. And by a lot, I mean quite significant, because the length of these struts are actually not very long, yet they have to withstand a significant amount of load. So again, what design stress value should I use? Should I use 10 or 20 MPAs before? Well, this is where going to the IIW does help. I looked through the category of categories of welded joints to see which one would be most appropriate. And here we can see a range which are fairly consistent with what I was looking at. And it ranges from 36 up to a fat of 50. And when I consider how we're going to fabricate this, I thought, well, a good value to use would be somewhere in the region of 40 MPa. So I decided to use 40 MPa as my guidance. And as you can see here on the top right, I altered the scantlings until in the FEA I got that 40 MPa. And then the construction drawing, I specified again the use of HeliShield and specified a particular detailing of the joint to allow the fabricator to get a good quality weld. But also after that, I went down on the shop floor to inspect, to make sure that the weld bead and the welded joint is approximately as I expect and as I designed it. You can't just sit in your air-conditioned office and assume it's going to be okay. So of course, it's all about attention to detail. And we can see here, there is not just one, but two saw cuts. It's bad enough having one, but why on earth are there two? And why on earth have they continued? Because you can see here on the left, they've already started to fully weld the member into place. And not only that, they haven't even bothered to perform the weld return around the mouse hole. But hey, who matters? What matters? Because we built a class. It's all quality. And so just like any good spaghetti western, it has a smattering of good actors. And of course, we can always recognize those good actors, just like we can recognize good quality. Just like here and here. We don't need to be an expert to see this is actually some very good, visually acceptable quality. And again, just like poor quality actors, we can easily see poor quality fabrication. Look at this beauty. There's cold blobby weld, there's soot everywhere, and there's a saw cut. It's appalling. What about here? It's too numerous to mention, but the most obvious one is, look how thick the bridge is for the butt weld. And not only that, there is no mouse hole. So as the fabricator is inside, welding those two plates together, what's going to happen? He's going to fuse the bridge into that butt weld. And so when he has to come to break it, not only is he breaking the actual weld that it's attached to, and as you can see, it's a very large, heavy weld, which is a problem in itself, but it's also going to be breaking the actual weld that's supposed to be the structural joint as well. Terrible. And here's another fine example. Poor welding sequence and planning created a very, very distorted structure. So much so that it was just not only visually unacceptable, but even class said, sorry, you're going to have to do something about this. And so the shipyard decided to put lots of crisscrosses everywhere to use heat to pull back the distortion. Well, that's the first golden rule of aluminium. Never, ever use heat to correct the structure. Never. And then, of course, the resulting view is just appalling. Just appalling. And look at this gem. They decided to try to weld up a slight misalignment. It got worse and worse and worse. When does it stop? It's just appalling. So when I was thinking about how to summarize all of this, is it about the design? It's about the fabrication? Is it about fatigue? Well, in reality, I could sum all this up in one word. Quality. Through the entire spectrum of whatever it means to you. Because quite simply, it is the real glue that holds the whole process together. It is not, it's the responsibility of everyone in the shipyard, and it's certainly not the responsibility of the surveyor or class. Thank you.